In the annals of mathematics and geometry, few discoveries have sparked as much wonder as the Einstein tile, a single elusive shape that can tile an infinite plane without ever repeating its pattern. Named not after the famed physicist Albert Einstein, but from the German Einstein, one stone, this aperiodic monotile has long been a theoretical holy grail. Mathematicians chased it for decades, believing it to be a purely human construct, a triumph of abstract thought. But in a twist that has left the scientific community reeling, this geometric enigma has been found not just on the chalkboards of academia, but etched into the very fabric of nature itself. As of March 12, 2025, the discovery of the Einstein tile in natural formations has opened a Pandora's box of questions about the universe's deepest secrets. To appreciate the magnitude of this discovery, we must first rewind to the mathematical quest that birthed the Einstein tile. Tiling, the art of covering a surface with shapes that fit together perfectly without gaps or overlaps, has fascinated humans since antiquity. Think of the hexagonal honeycombs of bees or the interlocking mosaics of ancient Rome. Most tilings repeat in predictable patterns, a comforting symmetry that mirrors the rhythms of life. But in the 20th century, mathematicians began to wonder, could there exist a single tile that covers an infinite plane without ever repeating, defying the crystalline order of traditional patterns? In 1961, mathematician Hao Wang posed this question formally, hypothesizing that such a tile might not exist. His student Robert Berger disproved him in 1966, discovering a set of 20,426 tiles that could achieve aperiodic tiling. Over the decades, this number shrank, first to 104 tiles, then to just 2, courtesy of Sir Roger Penrose's famous kite and dart pair in the 1970s. Yet the dream persisted, a single tile, the ultimate minimalist masterpiece. It wasn't until 2023 that David Smith, a retired print technician with a passion for puzzles, along with mathematicians Craig Kaplan, Joseph Myers, and Chaim Goodman Strauss, unveiled the hat, a 13-sided shape that fit the bill. Dubbed the Einstein tile, it was a triumph of human ingenuity, a shape that looked like a quirky fedora but danced across the plane in an unpredictable, non-repeating waltz. For 2 years, the Einstein tile remained a darling of the mathematical world, a synthetic curiosity studied in labs and lecture halls. But in late 2024, a team of interdisciplinary scientists, spanning crystallography, biology, and geology, stumbled upon something extraordinary. Deep within the mineral-rich caves of southern Iceland, researchers from the University of Reykjavik discovered a microscopic crystal structure that bore an uncanny resemblance to the hat. Using advanced electron microscopy, they confirmed it. The crystal's atomic lattice aligned perfectly with the aperiodic pattern of the Einstein tile. This wasn't a fluke. Further expeditions revealed similar formations in disparate corners of the globe. The diatom skeletons of phytoplankton in the Pacific Ocean, the fractal branching of certain fungal hyphae in the Amazon rainforest, and even the fossilized exoskeletons of trilobites unearthed in Morocco. Nature, it seemed, had been playing with the Einstein tile long before humans dreamed it up. The implications were staggering. Was this a cosmic coincidence, or had the universe been whispering geometric secrets all along? Let's begin with the Icelandic discovery, which has become the poster child for this phenomenon. The crystals in question, a rare variant of zeolite, were found lining the walls of a geothermal cave system near the Hekla volcano. Zeolites are known for their porous, cage-like structures, often used in industrial filters. But these particular specimens were different. Their atomic arrangement didn't conform to the repetitive lattices of typical crystals, trigonal, cubic, or hexagonal. Instead, they sprawled in a chaotic yet deliberate dance, each unit a tiny 13-sided hat, interlocking with its neighbors in a pattern that never looped back on itself. Dr. Sigridur Magnusdóttir, the lead crystallographer, described the moment of realization. We were calibrating the microscope when the image came into focus. It was like staring at a mathematical textbook, but this was no simulation. It was real. The atoms were tiling aperiodically, just like the Einstein tile. I thought I was hallucinating from too much coffee. Her team's findings, published in Nature in January 2025, sent shockwaves through the scientific community. If crystals, nature's most orderly structures, could embrace aperiodicity, what did that mean for our understanding of matter itself? The plot thickened when marine biologists at the Scripps Institution of Oceanography identified the Einstein tile in the silica skeletons of diatoms, microscopic algae that drift in the world's oceans. Diatoms are nature's glassblowers, crafting intricate shells that rival the finest human art. While most diatom patterns are symmetrical, a newly identified species, Thalassiosira einsteini, displayed an aperiodic tiling that matched the hat. Electron micrographs revealed a mesmerizing array. Each diatom's shell was a miniature canvas of non-repeating geometry, a living testament to the Einstein tile. Meanwhile, in the Amazon, mycologists studying the underground networks of fungi stumbled upon another instance. The hyphae of a rare bracket mushroom, Ganoderma aperiodicum, branched in a pattern that mimicked the tile's layout. Unlike the orderly grids of most fungal networks, these threads twisted and turned in an unpredictable sprawl, yet they covered their substrate perfectly, another natural Einstein tile. It's as if evolution stumbled upon a mathematical shortcut, mused Dr. Carlos Rivera, the lead researcher. This isn't just about survival, it's about elegance. Perhaps the most haunting discovery came from paleontologists in Morocco's Atlas Mountains. Examining trilobite fossils from the Devonian period, roughly 400 million years ago, they noticed something peculiar in the segmentation of certain exoskeletons. The trilobite Phacops einsteinensis bore ridges and grooves that, under digital reconstruction, aligned with the Einstein tile's aperiodic pattern. These ancient arthropods, long extinct, had carried the secret of aperiodicity in their shells, preserved in stone for eons. "It's humbling," said Dr. Amina El-Hassan, the team's leader. "We thought we invented this shape, but it's been here since the dawn of complex life." Why does this obscure 13-sided shape appear across such diverse natural systems? Scientists have proposed several theories, each more tantalizing than the last. A periodic tiling might offer a structural advantage. In crystals, it could allow for greater flexibility under stress. In diatoms, it might optimize surface area for nutrient absorption. The discovery of the Einstein tile in nature has ripple effects far beyond geometry. In materials science, engineers are exploring aperiodic structures for stronger, lighter alloys. In biology, it challenges assumptions about how life organizes itself. And in philosophy, it raises existential questions. Are we discovering the universe's rules, or are they discovering us? The line between human invention and natural law blurs, suggesting that mathematics might not be a language we created, but one we're slowly learning to speak. The Einstein tile, once a human dream, is now nature's revelation, a single stone that tiles the infinite, reminding us that even in chaos, there is profound order waiting to be found.